So a math sequence is basically a sequence of numbers that have a pattern, right? Just to kind of give you the general form of it. So sequences, there's a relationship between like the first pattern, the first term, the second term, or the first two terms and the third term, and so on and so forth. Just notation-wise, when we write curly bracket and then a sub n, that means we're just writing one of the terms for any n. So n is an index. Okay, so sequences are going to have an index. Okay, so, or basically a counter. So the index is our n, or sometimes, you know, it's our counter. And a lot of times we'll say, what's the first term? And it'll be, if we write it from 1 to infinity, that means it's an infinite sequence. And then if we get up until, you know, a certain number, then that means we're talking about that many numbers of terms in the sequence. Okay, so for example here, I can rewrite this as A1, A2, that means it's an infinite sequence. And if I say write the terms of the explicitly defined sequence, I mean give me the first few terms. Okay, I didn't specify exactly how many terms. So for here, if I want to say what is A1, so A1 is going to be 2n minus 1 over n plus 1. Well, what's n? N is 1 for A1. Okay, so for example, this one, A1, would be equal to 2 minus 1 over 1 plus 1. So we get 1/2. A2, same thing. So 2 times 2, which is 4, minus 1 over 2 is 1. So we get 1, 3 over 3. See what I'm saying? Is this coming back to you guys? A3, so 2 times 3, so 6, minus 1 over 3 plus 1. So I end up with 5 over 4. And A4 would be equal to 4, 8, 7, 7 over 5, and so on and so forth. So the first few terms you can say are, and we write them with commas in between. 1/2, we don't write summation. 5 over 4. Okay, same thing if I want to write this one. This would be basically my B1, B2, B3, B4. Of course, if I want to write B5, we can figure it out as well. If you do this, you're going to get 2 to the power 1 minus 1 over 2 squared. I'm sorry, 2 to the power 1, this is over 1. So just the first term will be 1. So B1. And then B2, 2 squared. So 4 minus 1, so 3 over 4. And then B3 is 2 cubed, so that's 8 minus 1. So we got 7 over 9. Next one, B4, 16 minus 1. So we end up with 15 over 16. And if we want to go to B5, we can do that as well. So we got 25 minus 24 over 25. Okay, so if you were given the pattern, and we try to tell, not the pattern, like the sequence, the actual first few terms, and we ask you to figure out, you know, what is the nth term, that's when you give this. So if you were given the list of them, and you're trying to figure out, you know, what is it? So some famous ones are recursive sequences, geometric sequences, and arithmetic sequences. Okay, the ones with the common ratio or the common difference. Is that coming back at all? What's the famous recursively defined sequence? Do you guys remember? At all? Fibonacci sequence, yes. Does anybody remember what it is? It's a recursive one. The Fibonacci sequence goes 1, 1, 2, 3, 5, 8. Mm-hmm. Yes. So you add the, so you add the first two numbers. So you add 1 plus 1, you give 2. Then 1 plus 2 is 3. Then 2 and 3 is 5. Then 3 and 5 is 8. Then 5 and 8 is 13. Right? And you keep going. So in a similar fashion, we can make up any other type of recursive sequence. So for example, this one is dependent on a1. So a1 is equal to -1, and a10 is 2a sub n minus 1. So a sub n minus 1 means the one before this n. So let's look at a2, for example. So if I want to figure out a2, that would be equal to 2a1 plus 3. Well, what's a1? That has to be given, or else we can't figure this out. So this would be equal to 2 times -1 plus 3. So we end up with 1. Then a3 is 2 times a2, right? Because 3 minus 1 would be 2, and then plus 3. So it would be equal to 2 times this previous one that came from here, plus 3, and that gives me the 5. Is this clear? So this would be 2a3 plus 3, which would be equal to 2 times that 5 plus 3. So we end up with 13. I like using the different colors so you guys can see what's being plugged in where. So if I want to write the first few terms of the sequence, or the first 4 terms, therefore the first 4 terms are, don't forget the -1, we start at -1, and then 1, and then 5, then 13, and of course we can go on forever with this. Any questions? Yes. So recursive means it's based off of at least one that came from before. Yep. Recursive means that you're going to see an a sub n minus 1 or n minus 3 or n minus something inside here. Or sometimes you can even, it can even be a sub n by itself. No, it would be yeah, something previous before it. So it could be 1 or 2 of them. Okay, so look at this one. This is b sub 1 equals 5. So b sub 1 plus 1, meaning b sub 2, is k plus 1 over 2 times b sub k. Okay, so let's take a look at how to do this one. What do you think b2 is going to be? b2 is what? That's b sub 1 plus. So this index is kind of a little bit confusing. So it's b sub 1 plus 1, which means that k is equal to 1 in this case. So we started out with k equals 0 in order for us to get this b1. Does that make sense? So for here, for this one, this is k equals 0, because this would be b of 0 plus 1. And then for this next one, for b2, this k is equal to 1. And then for b3, k is equal to 2. You see what I'm saying? So we have to be careful with how it's defined. So b sub 1 plus 1, which means that it's equal to 1 plus 1 over 2 times b1. So this very first one that was given. So this would be 1 times 5. So this would be 5. Agree? Let's use a different color. All right, so then B2, sorry, B3, that's K is equal to 2. So it'll be 2 plus 1 over 2 times B2. And this equals 15 over 2. All right, let's do one more. So B4 is going to be equal to 3 plus 1 over 2 times B3, which is equal to 4 over 2, so 2 times B3, so the 15 over 2. So 2's cancel, we end up with 15. Okay, so then the first 4 terms of this sequence, so the first 4 terms of the sequence, even though we started our index at 0, are equal to 5, then another 5, 15 over 2, and then 15. Any questions on this? Okay, well, now that we know how to, write the first few terms, it's almost like functions, right? You just plug in the value. Okay, so we want to write the rule now. We have to be a little creative with this. We want to try to figure out the pattern here. So for A, what do you think? Hi, Sydney. You're back. What's going on with the first one? Yes, we are jumping by a -4. So I add 1 plus -4 gives me -3. -3 plus -4 is -7. -7 plus -4 gives me -11. So we recognize that. So let's go ahead and write this out. So I'm going to say my first term is going to be equal to 1. And the common difference between them is the -4. Okay? And this is a type of arithmetic sequence where you have this common difference. And the general rule is basically your next, or a sub n, is equal to the very first term plus n minus 1 times the common difference. So this is a general formula for figuring out the nth term. So in this case, and here, what do we have? We have a sub 1, which is 1, plus -4 times n, and then -4 times -1. So minus 4n, and -4 times -1, so plus 4. So it looks like 5 minus 4n. And we can test this out. So therefore, my sequence, my a sub n, is going to be equal to 5 minus 4n. Okay, so we can check it out. If n is equal to 1, 5 minus 4 is 1. If n is equal to 2, 5 minus 8 is -3. N is equal to 3. 5 minus 24. Wait a minute. 12. It'd be negative 7. And so on and so forth. So this works out. The common difference is basically what's the difference between this number and this number, this number and this number, this number and this number, right? So this is a common difference. Okay, and the common difference is basically the difference between a sub n and a sub n minus 1. Okay, and then there's a formula for where you can actually get this. But if you want for now, if there's a common difference, then the nth term is given by this one. So keep this one in mind. All right, let's take a look at the next one. I have minus 1 and then 1/2 and then minus 1/3 and then 1/4. So immediately everybody notices what? Alternating signs, which means that my a sub n is going to have a negative 1 to the power n in it, right? Negative 1 to the power n, and then this is 2, then 3, then 4. These are counting numbers. This is just like 1 over, so this is just n. And of course, test it out. When n is equal to 1, this would give me minus 1. When n is equal to 2, this would give me minus 1 squared, which is a positive 1, and then over 2. And when n is equal to 3, you'll see that you'll get the negative 1 over 3. Any questions on this? Okay, what about this next one? C. What do you see for C? We have 1/2, then square root of 2 over 4, then square root of 3 over 8, then over 8. So we notice a pattern here in the first three, and the pattern is what? Square root of n, you'll agree, over 2 to the power n. So we do notice that this is the square root of n, because this is 1, right, over 2 to the power 1, 2 to the power 2, 2 cubed, but then this gets messed up here. But if our pattern is correct, then it should reduce. Sometimes it reduces to the thing that you have, or to the term that you have right there. Okay, so let's check it out. So if n is equal to 4, let's test it. This would be the square root of 4, right, over 2 squared, or 2 to the power 4, sorry. So we have the square root of 4, which is 2, over 16, and that does reduce to 1 over 8. Okay, again, notice the denominator is 2 to the power 1. Any questions? So always check to make sure that you did it correctly. What about the next one? It's not so obvious. Ones and zeros with some negatives in there. So it looks like it alternates signs here, then skips, not really alternating signs. So again, this isn't too obvious, so I'll go ahead and just give it to you. It's something that we don't want to forget about, and that's trig. trig functions. N times pi over 2. So when n is equal to 1, sine of pi over 2 is 1. When n is equal to 2, 2 pi over 2 sine of pi is 0. When n is equal to 3, 3 pi over 2, negative 1. 4 pi over 2, we're at the 2 pi, we're back to 0, and then it starts repeating. Okay, so now we're going to talk about limits of a sequence. Okay, so ignore this AP Calculus reference here. Yeah. All right, so we're going to be looking at sequences that are, that converge, which means that they actually approach an actual limit or a limiting value. And then some of them are going to actually diverge, which means that they're going to approach infinity. Okay, so formally, if you want, here, let me highlight this. Okay, we say that if an, basically the a sub n is a sequence, such that f of n equals an for every positive n, then the limit of an is going to be equal to L, as long as that L is a number. All right, so let's take a look at number four here. I think we've done this one before, right? So here, if I consider an to be like a function, and I just treat it the same way as a function, then we'll see that this one actually approaches what? Do you guys remember what this approaches? Anybody? I'll give you a hint. Euler. We did it in terms of x instead of n, but it's still the same answer. This approached E, Euler's constant. Okay, so you can find the solution to this, where there's no room at all here to do it here. But you can find this we did before in the notes on L'Hopital's rule. Okay, so therefore we can say that it converges. So this sequence converges. Okay, how about this one? Let's take a look at this one. The limit as n goes to infinity of a sub n of cosine of 1 over n. Well, this is going to approach 0. Yes, we found it by using L'Hopital's rule, by setting y equal 1 plus 1 over x to the power x, right? And then we took the natural log of both sides, and then the x came out to the front. And then we moved the x to the bottom, and then we took the derivative. Yes, yes. Okay, so this goes to 0. So 1 over, so cosine of 0 is equal to 1. So again, we can say that it converges. Okay, so therefore a sub n converges. Okay, let's take a look at this one. If we take a look at the first few terms, what does it look like? The first term at n is equal to 1. We can graph these too. look at first few terms. So at n equals 1, we get 4. At n equal 2, we get 5 plus 1, so 6. At n equals 3, it's going to be 5 minus 1. N equals 4, we're going to get 6. And guess what? The sequence Bn is actually 4, 6, 4, 6, 4, 6. It just keeps alternating. Yes, exactly. So it alternates. The terms alternate forever, which means they're never going to convert to anything. Alternate. The sequence diverges. Okay. Now, if we were to draw these, we would draw them as points, like at n equals 1, at n equals 2, at n equals 3, and you'll just see it's 4, then it's 6, 4, 6, 4, 6. So you can visualize alternating dots, and then it just keeps going on and on and on as n goes to infinity. All right, let's look at this one, b. So if I take the limit as n goes to infinity of this, let's use a different color. All right, so if I look at the limit as n goes to infinity of b sub n, I'm not going to write b sub n anymore. Well, we'll just do it for one more time. Of 2n over 1 minus 3n. So these are the same degree, just like the before, or you can use L'Hopital's rule here, or you can factor out an n, right? So if I factor out an n, then it cancels with the n from here, and this is 1 over n. And so as n goes to infinity, this becomes negative 2 over 3. It's basically the coefficients of any questions on this? Questions? All right, let's take a look at the next problem. And here I give you a hint to use L'Hopital's rule because it'll be very useful to use L'Hopital's rule here. All right, so the limit as n goes to infinity of a sub n is equal to the same as the limit as n goes to infinity of n over 2 to the power n minus 2. Okay, now we all know that 2 to the power n is going to go a lot faster than this n, so you could argue it that way, but that's an elementary type of argument, and we don't want to use that type of argument. But just know that this grows faster to infinity, and this is going to be 0, right? It's almost like a small number divided by a big number. This does tend to 0, but we want to show it using L'Hopital's rule. So because this is infinity over infinity, then we can take the derivative. So the limit as n goes to infinity of 1 over, so the derivative of n is 1, and derivative of 2 to the power n is 2 to the power n times natural log of 2. That's the derivative of a dx, right? Derivative of a dx is a dx times natural log of a. Okay, and then the derivative of 2 is 0. We'll just put that there so no one gets confused with that too. All right, so now if I take the limit as n goes to infinity of 2 to the power n in the denominator, so this is going to go to infinity, 1 over a very big number. This is going to tend to 0. And therefore, n converges. What do you think is going to happen with this sequence? Yes, it is. Did anyone get the UT alert just now on their text messages? My watch is beeping. You heard it? Did you hear my phone? My watch? Oh, you heard the sirens outside? I'm like, what? My watch just vibrated. All right. So if we were to put the infinity, of course, this is infinity over infinity. So there's two ways that you can do this. If you did the calc one way, where you can factor out an n, and then you have a bunch of n's in the denominator. I'm sorry, n squared. Or you can also do L'Hopital's rule a few times. So we can say that this is going to be equal to L'Hopital's rule. So take the derivative of the top, which is 6n, minus 1. Derivative of the bottom is 4n. And then take the derivative again. So L'Hopital's rule again. And we got 6 over 4, which reduces to 3/2. And so therefore, AN converges. Yeah, it's the first Friday of every month. Okay, any questions on this? Good? Thumbs up? Maybe? All right, good. One person gave me thumbs up. All right. So to make things a little bit more clear, I want to show you some graphs here, because when you see the actual graph of a sequence, you'll start differentiating and understanding why, how this is kind of different than functions. When we talk about a function, we have like a continuous domain, right? So we connect the dots. With sequences, we don't connect the dots, right? So basically, you're just plotting points because n is an index, so it's like a counting number. So we start with the 1, then 2, then 3, and so on and so forth. Okay, and then there's some names that go along with them. So for example, we have a sequence here in number A. So it's a decreasing sequence, and you can see that it's getting closer and closer to 0, right? So this actually converges to 0. And then in B, you'll see that it keeps going, and it's kind of like can also converging to a certain number. And if we look at C, this is an alternating one. Keeps going up, down, up, down, up, down, right? So it's alternating between two numbers. I think it's between -1 and 1. And then D is the one where it just keeps increasing, doesn't have a bound, and it diverges. Okay, so let's look at some of the definitions here. So we have this following theorem, which is very handy. If a sequence AN, hello, I always click the the eraser instead of the highlighter. If a sequence AN is bounded and monotonic, then it is going to converge. So what do I mean by monotonic? Anybody know? Yes, only increasing or decreasing. I mean, it's right here too. Okay, so this is a theorem that I want you to keep in mind. So if it's bounded and monotonic, then we can say that it's convergence. And then what is the definition of monotonic? Again, a sequence is said to be monotonic if its terms are non-decreasing or non-increasing, meaning this would be the meaning of non-decreasing, and this is the meaning of non-increasing. Basically, it means that, they get closer and closer to a term. All right, so again, bounded above meaning that it's bounded by some number m, and where m is greater than all the terms in the sequence. Bounded below, that means that it's bounded by another number n, and this number is less than every other term that's in the sequence. And we'll say that it's bounded if it's bounded above or it's bounded below. Okay, so above, below, and what it means to be bounded. Bounded doesn't mean that it's bounded above and below. If it's either bounded above or bounded below. All right, so once again, let's approach these now with our new knowledge. So here, let's look at the behavior of this sequence. It looks like it is a decreasing sequence. Do you agree? Decreasing sequence. And is it monotonic? I would say yes. And is it bounded? I would say yes as well, because it keeps getting closer and closer to 0, right? It keeps going closer and closer to 0. Or basically, we can also say that 0 is less than all of the terms here. And so we can say it converges to 0. Any questions? All right, what about B? Is it decreasing or increasing? Of course, we can see that it's increasing, but it's also bounded. It's also bounded by, I think this is a 6 here. Yeah, 2, 3, 4, yeah. So the 6 is actually higher than all of the terms in this sequence. And so it's above, or just bounded. And it's increasing, bounded. So therefore, we're going to say that, is it monotonic? Okay. And so therefore, the sequence converges to 6. Okay, what about this one? Well, we saw this one. This is oscillating. Okay, is it monotonic? No. Is it bounded? And look at that. It looks like it's bounded above by 1 and bounded below by -1. Okay, so therefore, the sequence diverges. What about D? What are we going to say about D? Is it increasing, decreasing, or oscillating? Yes, thank you. So this is increasing. Is it bounded? No, it is not bounded. That is correct. Is it monotonic? It is monotonic. It's non-decreasing. So it's monotonic, but it's not bounded, so therefore we can't use that theorem, and it actually does diverge because it keeps getting bigger and bigger without a bound. So therefore, the sequence diverges. Just think about it. If we were to take the limit as n goes to infinity of the sequence, it's just going to keep going on forever. So it diverges.